Okay, so last time we were wondering, in our example, and remember this is all just an example, how can we enlarge this collection of sets that we can measure using lambda? So here's an idea using sort of our analysis way of thinking. Right now we can measure only the sizes of elementary sets, but maybe if you have an arbitrary subset of this interval, then you can try to approximate it by elementary sets, and then use your knowledge of the sizes of those approximating sets to measure the size of your arbitrary set. So here's my suggestion. If you have an arbitrary subset, A, of the interval 0, 1, then let's say that the size of A is going to be L if and only if there are sequences of elementary sets. So let's call them AN and BN. Such that we have ANs, the ANs always being inside A, and the BNs always containing A. And so let's have the ANs kind of go up to A, using that earlier notation. So that means they're nested, and the BNs come down onto A. And if that's true, then I guess it's automatic that we have this inclusion for all n. So I don't need to say this, right? Sorry. Okay, this sentence is not done. Let me think about that in a moment. So we'll say that the size of A is L if and only if we've got elementary sets, some coming up to A and some coming down onto A. So these nested, they union up to A, these nested and they intersect down onto A. And if you take the measures of these sets, the sizes of these sets, then that sequence of numbers, this will be a sequence of real numbers, converges to L, and also this sequence of numbers converges to L. And yeah, I think if I state it this way, then I don't need to say this part, since if the ANs are nested and unioning up to A, then they're all subsets of A, right? And if the BNs are nested and intersecting down to A, then they all contain A. So this should kind of remind you of when we were working with Riemann integrals, and we were using the idea of a lower sum and an upper sum to come up with lower bounds and upper bounds on what we think the integral should be. And then we were saying, well, if you look over all possible partitions and you find that the lower estimates can be brought arbitrarily close to the upper estimates, then whatever number they're getting close to, that will be the value of the integral. This is kind of a similar idea. So this sequence of ANs, which are subsets of A, this is a sequence of elementary sets, so we already have an idea of what is lambda of them. We have a way of measuring their size. And each of these numbers, lambda of AN, is going to be a lower bound and a possible underestimate of whatever should be the size of A. And each of these, lambda of BNs, since the BNs all contain A as a subset, each lambda bn is going to be an upper bound on what is the size of A. And if the sequence of elementary sets, if these two sequences of elementary sets can be chosen in such a way that the lower bounds converge to the same place as the upper bounds, then that place that they converge to is going to be defined to be the size of A. So here we are defining lambda of A. But this definition only works if there are such sequences, right? So this does not successfully take us to this situation. So this does not give us lambda on the entire power set, on all subsets of 0, 1, and then gives us a measure. It does not. It only gives us some collection. So let me define the set that is now the domain of lambda. So let's define, I guess I already used A, so let me call it A prime, an extended version of A, a further extended version, which is going to be the collection of subsets of here, such that there exist these sequences such that these converge to the same place. So one way to say that without mentioning L itself is to just say that there exist these sequences such that lambda of an and lambda minus lambda of bn converges to 0. So that would be a nice, elegant way to describe the condition here. Okay, something like this. There exist sequences A and Bn, elementary sets, so in the original script A, such that the sequence of ANs goes up to A, the sequence of BNs goes down to A, and lambda AN minus lambda BN. I guess I can write it this way, but that's probably going to be a negative number. That's kind of less pleasant. So lambda bn minus lambda an, that sequence goes to 0. And actually another way of writing this, since we noted in the previous video, I think, that when one set is inside another, like if A is inside B, then lambda of B with A deleted, lambda of B complement A, is lambda of B minus lambda of A. This lets us view this difference, lambda of bn minus lambda of an, since an is a subset of bn, this is lambda of bn with an deleted. We can view it this way. So here is a larger set than the original A, script A. This one consists of not only the finite unions of intervals, but it consists of those sets that can be reasonably approximated by finite unions of intervals from above and from below, kind of from the inside and from the outside. So people call these sets Jordan measurable. So the elements of this collection of sets are the Jordan measurable sets. So this is the collection of Jordan measurable sets. And now we have lambda defined on this larger set of Jordan measurable sets. So let's just look at an example of something of a Jordan measurable set, which was not one of our elementary sets. So let's take the set of 1 over n's. So this is an example. Let's say A is the set of these 1 over n's. Then A is, I'm going to claim that A is a Jordan measurable set, sorry. So I claim that it is a measurable set. a Jordan measurable set, but it is not one of our elementary sets. So you have to use this idea of approximation by elementary sets in order to decide what is the measure. Okay, so let's look at the second statement first. Why is this not an elementary set? Well, to be an elementary set, you have to be a finite union of intervals. However, there's no way to write A as a finite union of intervals. For each element of A, if you take the largest interval that it's contained in, then that will be the singleton interval. So for any given element of A, like 1 over n for a particular natural number n, the largest interval it's contained in is this interval, right? And A has infinitely many elements, so the only way to write A as a union of intervals would be as an infinite union of intervals. There's no way to write it as a finite union of disjoint intervals. Okay, so definitely it's not one of the elementary sets. Now, what do you think is the measure of A? What do you think is the Jordan measure? That's what this would be called, by the way. Jordan measure. So remember I told you there are two components of what we're studying. There's the thing here and the thing here. How to measure and what it is that can be measured. So the thing here is called a measure, and the one we're looking at in this example is a Jordan measure. And the thing here, what can be measured? Well, I told you a couple of videos ago that this will be called a sigma algebra. But in this particular case, this ends up not being a sigma algebra, which is one of the problems with it. But we're going to define that later. Okay, so what do you think is the Jordan measure of A? So maybe pause the video and come up with a guess, and then come back and look. And here's the answer. We should get that the Jordan measure is 0. And maybe you can think intuitively about length. Like A is a collection of little dots, right? It consists of 1, 1/2, 1/3, etc. And each of these is a little dot and it has length 0, right? So it feels like if you just union up a bunch of dots of length 0, then you should get something of length 0. But that doesn't quite make logical sense right away, because, I mean, isn't everything just a union? Isn't every set just a union of all of the dots that it's made out of? Isn't the entire interval 0, 1? Isn't any interval, like AB, whose length we decided should be B minus A, isn't it just a union of the individual dots that it's made out of? But somehow it feels right still that for this particular set, it feels right to think that it has measure 0. Well, okay, so how would we come up with a proof? So we need a collection of elementary sets, a sequence of elementary sets that comes, maybe I should call it Bn for consistent notation with what's being said above. That comes down onto A, such that when you take the measures of these elementary sets, that goes to 0 as n goes to infinity. So this is what we'd have to show, that there exists a sequence of elementary sets nested, so their intersection is A and their measures go to 0. You could say they're Jordan measures, but this would be the measure in the sense of the measure of an elementary set. So this kind of thing defined here. Okay, so how would you show that there is such a sequence of elementary sets? Well, I mean, you could. So here's a picture. Let's start with 1, then 1/2. Let's say 0 is over here. then 1/3, 1/4, and something like this, right? And the dots kind of pile up onto there. So what you could do is, so for each bn, it needs to contain a, right? Each of the bn's we define in our sequence of elementary sets needs to contain a, so it needs to contain all these dots, and each bn needs to be contained in the previous bn, and we need the total length of the bn's to go to 0 as n goes to infinity. So maybe your first one could be like this. It takes a certain amount of stuff here, and then for all that'll capture all but finitely many of the white dots, and then for all the other white dots, just make a little interval around each one. Something like this. So that could be your B1. Then your B2, you could shrink this down. Then you have more dots to cover, but you're also free to make these intervals as small as you want, so make them even smaller. And so on. It's definitely not obvious that this is going to work, but you can show it. And I'm not going to show it because this should remind you of something that you probably did in 118b, no matter who taught you 118b. This is just a really standard problem that comes up. So here I'm looking in the old textbook by Abbott in Chapter 7, the Riemann integral. And this is an exercise that is very likely to have been assigned in some form, where you've got the function that takes the value 0 on the interval 0, 1, everywhere except at the 1/n type points. So 1, 1/2, 1/3, etc., where it takes the value 1. And then you're trying to show that it's integrable and compute the Riemann integral. So you end up in a very similar situation, and you draw the same exact picture, right? Except now your bn's you're thinking of as partitions, right? But you're faced with the same kind of problem. It really is the same kind of problem, where you're trying to sort of shrink this first interval down and shrink these other intervals down accordingly in such a way that the lengths of these, which end up being the upper Riemann sums, go to 0. So this is pretty much a problem that we've done before, just different notation, different language, different way of reaching the problem. In the end, it's the same problem. Okay, so I just wanted to show you an example of something that is Jordan measurable, but that was not an elementary set. So while I haven't done a proof, hopefully it's sufficiently convincing that one could do it. Okay, so have we actually, so we've extended this, right? But have we extended this to be all of the power set of the reals? Is it now everything? Are there sets that are not Jordan measurable? There are sets that are not Jordan measurable. So this has not extended to cover everything. Example, if you take the rationals in the interval, in the unit interval, so that it's one of the sets we're thinking about, then that is going to be not in here. It's not going to be Jordan measurable. So remember, Jordan measurable means basically can be approximated from above and from below by elementary sets, finite unions of intervals, in such a way that in a consistent way, in such a way that the measures coming from above and the measures coming from below meet up. So I claim that for this set, the set of rational points in the unit interval, it's impossible. And here's the reason. So before we think about sequences of elementary sets, let's just imagine we have an elementary set A, which is below, and an elementary set A, which is above. So by that I mean a subset and a superset of this thing. So if you have a subset, remember, elementary sets are supposed to be finite unions of intervals, right? Where interval means any of these types. Any of these types here. So if I have this finite union of intervals, which is a subset of this, well, an interval, if it's not empty, then it's going to consist of, okay, so an interval can be empty, right? Or it can have one point in it, or it necessarily has irrational points, right? So an interval with more than one point in it, an interval other than one of like this type, this would be an interval with one point in it. But any interval that's bigger than this, that has more than one point, is going to have some irrational points in it, because by their nature, intervals have the property that if you have two things in an interval, then anything in between is in there. Sometimes that's used as the definition of interval. And the real numbers have the property that if you take any two real numbers, there's an irrational number in between. So if you write A as a union of AIs, where the AIs are all among these four types of intervals that I'm allowing, then all of the AIs have to be one-point sets. All AIs are singleton sets. And so, or empty, right? I guess the empty set counts as an interval in our setup, since I allowed us to write things like this. That would be the empty set. So regardless, singleton sets or empty sets, their Jordan measure is 0, right? Because of our definition back here, that for all of these kinds of sets, the measure is the difference between the endpoints. It's going to be 0. So we just get 0. And so if A is written like this, then its measure is defined to be the sum of the measures of the AIs, so a sum of 0, so it's 0. So necessarily, if A is an elementary set that is contained inside here, then definitely its Jordan measure is 0. So then, Jordan measure of A is 0. And what about B? So let's think about writing B. Here, B is in here. It's an elementary set, so it's a union of intervals, a finite union of intervals. Sorry. Like that, where the BIs are coming from here. Then if okay, so let's draw a picture for this. Let's say this is the interval 0, 1. Then these BIs, they're elementary, or they are intervals, sub-intervals of the interval 0, 1. And let's say they look like this, like B1, B2, B3, and then maybe there's a gap, B4, B5, maybe another gap, something like this. So this is a finite union of intervals, that's B. And what I want to argue is that there cannot be any gaps. So maybe it could be something like 0, and then this point is A. Sorry, we have to include 0. Union A, and then the next one, B, union, and so on. So we could have little left out points, but I claim that we cannot have gaps of finite size here. So in this picture, these are the individual b's, the intervals that b is made out of. And I say we cannot have a gap of non-zero length here, because if we did, then there would be an irrational, or there would be a rational number in there, right? And that rational number would get excluded from b. But b is supposed to contain all the rational numbers from 0 to 1. So, okay, that's not really a rigorous argument. I think to make this rigorous, you would have to sort of write down exactly what are the endpoints of the bi's and then put them in order, and then argue that they have to go end to end. Even though they can skip points between them, they have to go end to end. Proof by contradiction: if there were two endpoints in your ordered list of endpoints that did not match up, that didn't go end to end, then there's a rational number in between, and that leads to a contradiction. Okay, but hopefully it is believable that they go end to end, and so when you take the sum of the lengths of all of these, you get a telescoping sum, and you just get length of 1, right? If there are no gaps allowed, then the length of that blue part is going to be 1. So lambda of b is just going to be 1, no matter what. Okay, so I'm going to consider this all to be part of the informal example so that I can get away with anything. Okay, so with what we've got now, it's pretty clear, I hope, that there's no way you're going to come up with a sequence an building up to a and a sequence bn going down to a, where a is sorry, I never called that a. It's just called this. You're never going to be able to build a sequence an going up to this. And a sequence bn coming down onto it. With the property that the lambda of an's converges to anything other than 0. The lambda of bn's converges to anything other than 1. You always have, so if you have this, then you'll always have lambda an. It's just going to be the constant 0 sequence, so it converges to 0, and lambda bn converges to 1. It's the constant 1 sequence. So definitely this is not a Jordan measurable set. So our ultimate goal in measure theory is going to be to define a map like this that measures the sizes of sets. The map, so in general, we'll usually use mu for the map rather than lambda, and that will be called our measure. And we want this to be a large set. We want it to include a lot of things, and we want lots of reasonable properties to be satisfied. Things like this, you know. If you have two disjoint sets and you take the measure of their union, then that should be the sum of the measures. Things like that. So we're going to first focus on what kinds of things the class of sets here can be. Oh, and just to clarify that point, our goal is not to just define one map here that works, or define one collection of sets here and one map that works. No, our goal is actually to develop a general theory of these maps. So a general theory of measures and of sigma algebras, which I'm pointing here. This is not a sigma algebra, but that's what will end up here. So we want to be able to do this also not just for the reals. So here we were focusing on subsets of the unit interval, but we want to be able to deal with arbitrary sets, just like in the early days of 118, or the later days of 118b. We were focusing on metric spaces in general, right? Putting metrics on general sets. Here we're going to be interested in putting measures on general sets.